Orlando Yang, and I will be talking about how linear algebra can be applied in direct current circuits. So, many electronic devices, such as phones, laptops, and even your fridge, all rely on circuits. But how do engineers design them? Turns out, linear algebra is a fundamental part of it. Today we will use Kirchhoff laws to solve a circuit with linear algebra. So first of all, we have to talk about the two Kirchhoff rules, the Kirchhoff loop rule and the Kirchhoff junction rule. The Kirchhoff loop rule states that the sum of voltages across any closed circuit is equal to 0. And the Kirchhoff junction rule states that the sum of currents at any junction will equal to 0. Okay, so this will be the circuit that we will be working with. It has a electromotive force of 10 volts, resistor 1 of resistance 2 ohms, and then resistor 2 and 3 in parallel of resistance 4 ohms and 1 ohm respectively. And these three currents, current 1 is going to the right, and it splits into current 2 and 3, and then here they combine back into current 1. So after establishing all of that, our main objective now is to find the value of I1, I2, and I3. Let's first look at the Kirchhoff junction rule. So the Kirchhoff junction rule states that the current in is the same as the current out. So we can look at this junction, for example, and here we could see the current in, which is I1, will equal to the current out, which is I2 plus I3, and that's our first equation. We'll be moving on to the Kirchhoff loop rule. So this one was the junction rule. Let me write it down. And now this is the loop rule. Loop rule. So first of all, we will look at the loop, this first loop here. This way, we will be looking at that loop first. So for that loop, it will be the electromotive force. So we're going to be adding all the voltage together. So the first voltage is the electromotive force, and then this is the second one we encounter, minus the voltage across this resistor, according to Ohm's law, will be current times resistance. So the voltage across the first resistor will be I1 R1, and then you go through the second resistor, and the voltage through the second resistor, also according to Ohm's law, will be I2 R2. So that's all the voltages across this first loop, and you set it equal to 0. And now we look at this loop, this one. This is the second loop we have to pay attention to. And for that one, as you can see, you go here, and the first one we come across is the voltage drop across the third resistor, which will be negative I3 R3. And then here you actually go backwards through the second resistor, so you add the voltage, so plus plus I2 R2. And now that that loop is complete, you can set it equal to 0. And the way we got the IR is through Ohm's law, which says that voltage is equal to current times resistance. Exactly what we need. Since the problem showed us that resistance 1 is 2 ohms, resistance 2 is 4 ohms, and resistance 3 is 1 ohm, we can substitute the R's into these. Oh, and we could substitute EMF equals 10. So first of all, this one, we can move everything to one side for the junction rule. I1 minus I2 minus I3 equals 0. And this, for the second one, we can do 10 because EMF is 10 minus I1 times R1, which is 2, so we get a 2 I1 minus R2 is 4 I2 equals 0. And the third one, we can do R3 is 1, so just negative I3 equals 2, plus 4R2 equals 0. And yeah, so you can you can simplify the second one even more into negative 2I1 minus 4I2 equals negative 10. And you can just make all these positive. And there you go, you have a system of 3 equations. And you can put that into matrix form. AX equals B, where A will be 1, negative 1, negative 1, and this will be 2, 4, 0, and this will be 0, 4, negative 1. Oh wait, this thing should be I2. Sorry about that. Right, that's matrix A, and matrix X is I1, I2, I3, and B will equal to this right side. So it will be 0, 10, and 0. 0, 10, 0. And there we go. We will have a matrix to solve for. Now we can start solving this. First of all, we can turn it into an augmented matrix like this. Right, and then we can perform our elementary row operation. Here we do negative 2 times row 1 and add it to the second row. So row 1 stays the same. Here, negative 2 times 1 is negative 2, you add it, so this will be 0. This one will be 6. This one will be 2. And this will be 10. And this last row remains the same. And then this will become 1, -1, 0. We can simplify this one first. And we could swap these two rows. So it could be 0, 4, -1, 0. And divide this one by 2. 0, 3, 1, 5. And now we can do what is it? Oh, we could divide this by 3 again. Oh, I guess we can change this. It'll be kind of ugly though. It'll be 1/3, and 5/3. That we'll have to do. Alright, so we'll do -4 times the last row plus the second row and replace it with the last row. So 1, -1, -1, 0, 0. Oh wait, no, this will change. 0, 1, -1. Alright, so we do -4 times 1 plus 4, -0. -4, that will be -4/3. And then -1, that would be -7/3. And this one, -4, so -20/3. So we almost got that one down. So what we can do here is we can what is it? We can divide both sides, or divide this last one by, multiply it by -3/7. So this time -3/7 is 1, and this time -3/7, 20. It would be 20/7. So you would get 1 and -20/7. Yeah, so then we just add row 3 to row 1 and row 2. So row 3 would still be this. And row 2 would be 0, 4, 0, -20. And this will be 1, -1, 0, also -20/7. And then we have one more. 0, 0, 1, -20/7. Here we can divide, we could divide the second row by 5. That would be 1, this would be 5. And we can add the first and second row. Second row stays the same, -5/7. Third row, if you add them, 1, 0, 0. Add these two, -25/7. And we reduce this side to REF, RREF, I mean. So from this, what we can take away is that the one here stands for I3 minus 20 over 7 equals 0. The second one is I2 minus 5 over 7 equals 0. And I1 minus 25 over 7 equals 0. So what we take away from this, I1 equals 25 over 7. I2 equals 5 over 7. And I3 equals 20 over 7. And we found the exact value for the three currents. Is a practical application of linear algebra.